the design sensitivity. And even so, we can actually on the right see that the horizon redshift across mass spectrum, the best we can do is really just at redshift 3, which arguably is still further than many other surveys, but it's not really that far away if we compare to the other detectors that I will talk about. Now you can, of course, this is only the resolved binary, and then we can do a further thing is that we can combine the weak signal in the stochastic background, and that may help a bit, but not that much. And here is a detailed study on that. And that means when we compare to the possible sources in terms of the merger race density as function of redshift, we can really detect local sources that are the remnants of the so-called population 1 and 2 stars in the later universe. So for example, in the denser cluster or in an isolated binary evolution in galactic field. So this will be this curve, the orange and blue. And you can see that when we add the LIGO sensitivity horizon, so we are really just looking at the peak there. But then there are lots of things we can actually probe for higher redshift. And it's really the treasure is hidden in these high redshift population. For example, the green one is the binary black holes that originates from the first star generation, or we call population 3, or the metal 3 stars. And also, of course, in cosmology, we care a lot about the primordial black holes that are not even stellar remnants, but the relics of the early universe. And I will talk about it in more detail later. So, and then to really see the treasure, we actually need the next generation detectors. Of course, they are next generation, so meaning that they will be constructed at least like 2030s or so. So there are two promising proposals. So one is the Cosmic Explorer in the States, which is it's just 10 times larger than the current LIGO. So it's like 40 by 40 kilometers. And then the second one is the Einstein telescope, which is an underground facility in an equilateral triangle shape and with 10 kilometers. So, so these are really much larger detectors, which we hope to build, and that will greatly improve the sensitivity. And by improve the sensitivity, I really mean like they are almost factor of 10 better than even the design sensitivity. And if you compare the current sensitivity, there's O3, the gray curve here. So it's like, even like perhaps 20 times better than the current sensitivity. And in terms of the redshift horizon, so we can extend from redshift 3 to up to like almost redshift 100, or at least order of redshift above 10 or so, depending on the masses, because as we know, the gravitational wave amplitude is depending on the mass. So we have different horizon across the mass spectrum. And that's great. And then as some advertisement, so what's the prospect of these next generation detectors? So so recently, we have published a Cosmic Explorer Horizon study, which is NSF funded, and I'm part of it. And we actually have discussed a lot of different science goals that can be achieved in Cosmic Explorer or the next generation detectors era. And the Einstein telescope is also put into a more official roadmap on the research, the so-called research forum, European strategy forum on research infrastructures, which is some sort of official organization that put Einstein's telescope forward. Okay, so those are really the observing scenario we expect in the next generation detectors. So we are now back to the two interesting populations at high redshift. So again, the first one is the binary black holes originates from the population 3 stars. So why we are interested in this because they are metal free. the population-free stars are metal-free, and we expect them to form more massive black hole remnants after supernova collapse. And that is also related to so-called light seed formation scenarios for the supermassive black holes. And I think Fabio is recently has some studies on that. Also, related to cosmology, they can be also sources of the reionization, for example. So, if we can use the binary black holes of these population-free stars as tracer, and that would be great. And we can try to also study some of the binary formation in a very different scenarios in the metal-free environment as compared to the population 1 and 2 stars. And then for the second class is the primordial black holes. Well, we are interested in it because they are relics of the early universe, and the merger rates of that is actually related to the details of the initial density fluctuations, or even some sort of theories of the inflation and details in the inflation, and which is good because now we can have more probes to learn about the early universe in addition to the CMB analysis. And of course, if you ask cosmologists, they will also argue that primordial black holes can be dark matter candidates, or at least part of it. So that's why we are also interested in looking for these primordial binary black holes. So let me first start with the population-free binary black holes and what's the observing scenario and some sort of background of that. So actually, well, we know that there are lots of theoretical uncertainties in terms of their formation of the binary black holes originated from population-free stars, because first, we don't really understand what initial conditions of these protostars are to actually form the population-free stars. So for example, the distribution of the gas clouds in the primordial gases, of course, we don't really have a very good measurement. So there are some simulation studies to try to look for the effects of what if the gas clouds are distributed in a fewer numbers, but with a larger mass and also larger radius versus there are more but smaller gas clouds. So what will happen to the binary star formation? It turns out that these two scenarios can differ the initial orbital separation of the binary stars quite a lot, and that actually turns out to affect the binary evolution towards the formation of the binary black holes, and that would of course lead to a very different merger rates density that we can actually measure. And of course, the second uncertainty is that how the population-free star formation rates actually evolves. So in particular, is that first, so when was the first star actually born, right? So again, we cannot trace the redshift for the first star yet. So we rely on some theoretical estimation and some sort of cosmological simulation study, and which hints that they probably born at redshift below 50, but this is really kind of like a rough estimate. And the second thing is how does it evolve? Because again, that will also affect the merger rate density that we can observe at the end. And there are some constraints from the gamma ray burst observation due to the population-free supernova, but this is already like 10 years ago, and we don't really have much more constraint on that. Of course, like if JWST is online, then we may have more constraints from the crazy observations, perhaps. But given the best knowledge we have currently, and then if we ask computational astrophysicists, so including different scenarios in the initial condition and what the population-free merger rates would look like, and this is what it can look like. So there's a pop 1 and 2 merger rates, and then there are few curves that gives rise to the population-free binary black hole rates, and you can see that if you vary different initial conditions and it varies, really orders of magnitude in terms of the actual merger rate. But it's really subject to the theoretical uncertainty that we have right now. And in this study, Belchinsky 2016, they try to cover very different formation scenarios and conclude that it's still like with the theoretical uncertainties, so it varies quite a lot in terms, even in the absolute magnitude of the merger rate density. But as an observer, so let's have at least a mock data challenge to actually quantify, what if there's some moderately conservative rate from the population free and see how well we can measure that first, right? Because if we cannot really measure that, even for very large rates, then there's no hope to actually extract any further information from population free stars. And so it's really important to quantify the uncertainties there. So the setup is the following. So we take the simulation studies from the three major channels. So the first two, the blue and orange, is the so-called population 1 and 2 stars, either in a dense stellar cluster or they are just in the galactic field. And then for the third channel is what we are really interested in, is the population 3 binary black holes. And then for the simulation studies, let's assume a moderate rate. That is, the peak of the population free merger rate is 1/10 of the dominating channels at the low redshift, around 2. So with that, we only have about 2.5% of the population free binary black holes in total, around redshift 11 or so. And then we simulate 2 months worth of data in the next generation detectors network. And that actually gives us quite a lot of data as compared to now. So we will have like 16,000 of binary black holes. Of course, the SNR is also, are also much larger than the current SNR. And the redshift uncertainties is really less than 30%, and which is already like a factor of 3 better than the current measurement. And then we use like a statistical method called hierarchical Bayesian inference to measure the population free peak. And we do this with 2 approaches. One is the so-called model agnostic approach. We use Gaussian process regression to just map out the total merger rate density. And then for the second one is that we'll try to use some phenomenological function to infer details of each subpopulation. And what do I mean by Gaussian process regression is the following. So here is an example. So in this plot, this is the reconstructed merger rate density using the Gaussian process regression method. So that is to say we bin each redshift bin, and then so you see some wriggling there. So it's that for each bin we assume some. So for each bin we vary the merger rate density at each redshift bin, and then we just correlate each bin, and it's a fully data-driven approach to actually map out the total merger rate density. And as in this plot, you can see that with this model agnostic method, we can actually measure this peak and its location roughly about 50%. And that is to say, it's not like order of magnitude as compared to that theoretical uncertainty. So we are really pinpointing the peak at the population free pretty well, even if the actual rate is, it's just 1/10 of the dominating peak, and which is nice. And then we do a sanity check, is that in a second simulated universe, so we assume that there are no population free mergers, and then we just do the inference again. And then turns out that so there's still some fluctuation that maybe you think is a peak, but it's much less significant, and it looks like really a tail as compared to the case in previously where we do really see a peak structure there. And then the second approach is that we use a phenomenological model. So these are really the functional form for the 3 channels, and we try to so these functions are not really, they does not really carry any information about the actual physics. It's just, so as a first step, we really just try to measure whether we can measure it back the shape of each subpopulations. And it turns out we can, and especially when you look at the color band of the population-free mergers, so which is a green band. And again, we can, with the model approach, we can actually measure the peak in a more precise precision that is on the order of 10% or so. And and if you can see the previous plot, so this peak, if you compare to the other channel, which is the so-called field channels, so the binary, the isolated binary evolution in the galactic field. So this is really the noise floor that would maybe degenerate with the population-free mergers. So to quantify that, we vary the different relative fraction of the cluster binary versus the field binaries. That is to say, if this value is smaller, so we increase the noise floor of the tail beyond the high redshift regime, and then we try to locate or try to measure the location of the high redshift peak. And so here is the true value, so it's around 11. And then with the true approach, we still recovered quite well of the location of the peak. And that's to say, most of them are beyond redshift 7, which is good. So now we can really map our high redshift peak. And also as the noise floor decreases, so in this direction, and then we will get a better measurement as expected because the noise floor is lower. And then for the Gaussian process regression, as I said, so we just map out the total merger rate. So we use some peak finding with some restricted derivative tests to actually calculate the posterior of the peak location. And then in the phenomenological approach, we can actually infer directly the peak location because that's one of the parameters in the phenomenological models. And again, so the precision is like 10% to 50%-ish. And then, of course, the second quantity we are really interested in is the fraction of the population-free stars. So again, here is the relative fraction, and on the y-axis is the fraction of the population-free merger rates in total. And then we repeat the analysis with two set of universes. And one is with the population-free, that is, again, the 2.5% in total. And then the second set is the universe that without any population-free. And turns out that with 2 months of data, we can actually precisely measure the fraction with about 1%, on the order of 1%. And because everything just scales with 1/√n as the number of data grows. So we expect that within a few years, we can constrain much further down to order of 0.1% in terms of the merger rates peak and also the fraction, and which is good because now we can really, from these fraction and also the location of the peak, we can map it back to the detailed physics that governs the formation of the these population-free binary black holes, and maybe we can extract the detailed physics further. And this is what I just said. So once the merger rate density is measured, then we can trace back the progenitus rate, and then we can study the distribution of the initial orbital separations, etc. And then, so we actually have a study for the population 1 and 2, and I'm not going into details here. And if you're interested, we can discuss it a bit further in the Q&A. So this is really the one of the first study to actually quantify the observing scenarios, and because of the theoretical uncertainties, so we are still working on how to actually relate this back to the theory. And that would be some of the future work there. And any questions so far? Yes.
the modeling approach, I have no problem. I can understand that. What you call Gaussian regression.
Okay, yeah.
What exactly is it? Is it just binning and fitting a little peak, or is it more than that?
It's more than that. So it's sort of like a pre-machine learning method. Is that for each bin, we have a variable. So let's say we have 30 bins here, and then we will have 30 variables that characterize the height of each bin, right? And then we then apply a kernel, that is to say we correlate the adjacent bins, and then we just let the data tell whether the correlation, whether the correlated kernel can actually map it out the merger race density. So it's like actually, like, to me, I also feel like this is kind of a miracle. Why the data-driven approach can really give us back the things without any knowledge, but it turns out that the math says that okay, it can. So yeah, so it's some sort of machine learning.
So basically, the correlations you obtain from all the synthetic experiments you do.
Yes.
Once you have that correlation matrix, then you apply it to the real data.
Yes.
And you get this feature.
Yeah, exactly.
Okay, good, thanks.
Like, to me, it's still very amazing that you can do this with just the pure data. So yeah, I really love this method. Yeah. Okay. Any more questions before we go on? Okay. And then we can go to the second topic, that is the primordial binary black holes, which really means that we are now across the astrophysical boundary. So we look at the redshift beyond 20 or so. So yeah, and perhaps here is a list of differences in the black hole formation. So we are not even talking about binary black hole formation, but just focus on the black hole formation of these two channels. So I'm not going through the whole list, but really in a standard picture, so the primordial black holes, we should expect these black holes formed in a much earlier epoch, so even much before the CMB epoch. So in a standard picture, because there can be different suggested primordial black holes, which may be at a later time, but still, like, we expect them to be formed before the astrophysical regime. That is to say, even before any baryonic structure has started, and and because the astrophysical black holes are the collapse of the stellar of collapse of the stars, or even the hierarchical merger, that is to say, merge the black holes merge together to form a larger black hole. So we expect them to form in a much later time, like redshift below 30 or so. Now, so let's say now we have a bunch of primordial black holes in the early universe, and then there are some surrounding matters in it. So how did the primordial binary black holes are actually formed then? So I'm not going through all the details, because it turns out that we can actually do the detailed dynamics under Hubble flow, and actually so Rideau and all in 2018. So they actually developed the theory and numerical simulations that verify the theories very well. And here I just give a very broad overview. So let's say now we have so-called Poissonian binary primordial black hole population. That is to say, they are spatially uniform, but then their birth is so time of birth is following the Poisson distribution. And then, of course, that gives rise to some sort of nearest neighbor separation. From that, we also have so there are some initial density fluctuations around the surroundings, because the surrounding matter, including the black holes and also any dark matter over densities there, they are not exactly uniform. It turns out that that can generate tidal forces that would give rise to an angular momentum for the two primordial black holes pairing into a binary. So you can think of it as like there are some tidal force that harden the primordial black holes pair and then form a binary so that they can merge within the age of the universe, as we can see now. So this is really a one-slide picture of the formation of primordial black holes binary. So we can further discuss that in Q&A if you're interested. So the main results from the theories is that it turns out that we can get universal merger race density from this simple picture. And it turns out that that follows the cosmic time as negative power, which is constant. And in other words, that is to say, in the redshift domain, we will see a primordial black hole's race that would increase as the redshift goes. And at least that is within our observable horizon. Of course, like at the very, very large redshift, then we should expect there's a cutoff, but that is to say a redshift much larger than 1,000. And of course, even with Cosmic Explorer and Einstein telescope, we cannot observe that far. So there's this monotonic increasing merger race is a very distinctive feature comparing to the other channels. And the second feature is that beyond redshift 25 or even 30, so we really expect the primordial black holes to dominate the merger race because we don't expect any astrophysical black holes to form beyond redshift 30. And so there's some assumptions that if you're interested, I can come back later. And from so before we actually go to the next generation detectors regime, so we can actually do some current constraints from the second catalog, which we call the GWTC2. So, but then that comes along with a lot of caveats. So, but let's do the simplest thing is that, so let's just assume all the binary black holes in the second catalogs are primordial. Then what can we tell then? So first, we can always map the primordial black holes abundance back to the dark matter fraction. And it turns out that if we assume all the black holes in our second catalog are primordial, and that would give the upper constraint, that is the primordial black hole fraction as a dark matter is below 0.3% or so. But then if we want to do any constraints that is lower than this fraction, it's very challenging because now we need to include what is the astrophysical programs in the binary black hole mass and speed measurements. And in this case, the redshift, so in the second catalog, the redshift is not really useful because basically all the channels are increasing and you cannot really distinguish the slope very precisely. So that means subject to the model uncertainties. So we borrow some of the population synthesis simulations results. So we can pretty much lower the constraints by an order of magnitude. But it really relies on the interpretation of the outliers and whether the heaviest black holes are really inconsistent with the actual physical population, and then we can interpret it as a primordial black hole, etc. But of course, astrophysical black holes can also form a very heavy system. Like there's still a very hot discussion of this particular system, GW 190521, whether this heaviest black holes are astrophysical or not. But anyway, so the main question, the main takeaway is that why do we bother the local universe, right? Because primordial black holes, they should be something that's at much earlier epoch of our universe, and using the current measurements, so we are really shooting ourselves to the feet that there are lots of things to really take care into, and the evidence from the current data is not really that clean. And this is to remind again, like most of the primordial black holes, we expect them to dominate in the much earlier universe. And so in here, if we just want to have anything that is at the sub-percent level, that's very hard to do. And from that, that means, so we have to at least quantify what would be the high redshift binary black hole measurements in the the next generation detectors in order to give a more clearer evidence for the primordial existence and their abundance. And then, if you ask anyone that's not too familiar with the detectors, they may say, okay, so let's just wait for these detectors to turn on and then detect a high redshift binaries and then get an override. So it's not that easy because the signal to noise ratio, it turns out that it still decreases with the redshifts. And in gravitational wave detectors, we are not measuring the distance or redshift as good as any electromagnetic surface. And so that is to say, we need to quantify how good or bad the redshift measurements can be at the high redshifts in order to not confuse ourselves that our high redshift measurements are not coming from any astrophysical sources versus the primordial sources. And that's to say, we still need to consider possible contamination from the first generation stellar binary black holes or the population-free black holes. Then we first ask the question, so will we have a golden event that at larger than 30 in order to use this single measurement to prove the existence of the primordial black holes? And to do that, so let me just go through very quickly the redshift uncertainties we expect in the next generation detectors, assuming a uniform merger rates density first. That is to say, we just look at the likelihood and not look at without any concern with the astrophysical rates or primordial rates from the theories first. So here, so we actually find out that the optimal systems or the window of the mass window for probing the primordial black holes in the next generation detectors is between 20 to 40 solar masses. And here is the x-axis is the total mass in the source frame. And as a reminder, so with gravitational wave detectors, what we directly measure is the redshifted masses. So it's the mass times 1 plus c. And so we usually just, but then for our study, we want to look for which actual mass gives us the best constraint. So we plot this in the source frame mass that we are really interested in. And then for the y-axis is the redshift, and the violins corresponds to the posterior density, and then the bars are the 95% credible intervals. So that gives you, like, if you want to translate to a Gaussian error, it's like 2 sigma. And so here, so the two violins correspond to a different detector network, but the highlight is that between 20, like in these two systems, 20 and 40 solar mass, we can actually constrain the redshift. That is, the lower limit is larger than 20 if the true redshift is at 40. So that is a good sign because now at least we know the lower limit is not as low as 10 or even like below 10. And if that is so, then that would be bad because we cannot really distinguish whether this high redshift detection is really coming from the astrophysical regime or primordial regime. And so how do we quantify the evidence from these actual measurements? So now we need to take into account for the merger rates because it's a Bayesian statistics and the price is important. And for that, we do first a toy model for the merger rates first. So again, so this is the prior for the including the merger rates from the two populations. So here the peak structure one is the population-free merger rates density, and then the tail here is the primordial binary black hole merger rates. So as is the merger rates because we multiply with the volume effect because that's what we actually observe in the detectors. And you see a lot of field curves with different colors. So these corresponds to the relative height at this redshift 30. So there's to say by the green curve. So at at redshift 30, the merger rate is 1:1. And then, so we try different models that covers field orders magnitude. Again, so we don't really know the primordial black holes merger rates. So we don't know their normalization for now. So we try different models, which is still consistent with the current constraints. So that I have to emphasize. So here again, 30 is the critical redshift that we define it as the boundary between the astrophysical regime and also the primordial black holes regime only. So, and then I'll probably skip this slide, and then we go through a Bayesian analysis. That is to say, we calculate the evidence and then compare the evidence and calculate the base factor, and say we have a system that is 20 solar mass at redshift 40 with some inclination. And turns out that with such detection, we will actually favor a merger rate that is that has a large fraction of primordial black hole merger rates compared to the population-free merger rates. That's an astrophysical one. And then, so this model is much favored. That is to say, we favored a merger arrays that has a dominating fraction of primordial black holes at large redshift. And we can also further calculate what is the probability of this particular system that has a primordial origin. That is to say, what is the posterior mass below the curve in the white region. And it turns out that we can get a large significance there. So it's like 98% or so. Of course, it's not as large as 5 sigma, but still like, it still gives quite significant evidence, but not as a definitive evidence. So then, of course, we can still argue that this may not be significant enough. So, and then the next step naturally is just look at the population again. So this is what I did for the population free, and now we extend it to the primordial black holes. And again, we do the Gaussian process and phenomenological model, and and then there are some preliminary results that with 8 months of data at large shift, so we are precisely enough to measure to beat down this constraint in a down by an order of magnitude more. So here is again the reconstructed merger rates between the population free and primordial black holes. Again, so this is Gaussian process. So in here is clearer. So we really bin each redshift bin, and then we just recover the magnitude here. And as a future work there, so like we try to extend the mass and spin and redshift inference because in a joint inference, because all the studies I have talked about previously, it's really just the redshift measurements. And of course, we know that in different channels, we have very different mass and spin spectra, that these additional information would help quite a lot to pinpoint the merger rates density in a high dimensional data space. And that would definitely help to study more physics from that. So for example, in the primordial black hole scenario, with the spin measurement, perhaps we can study some of the accretion effects in the primordial black hole binary formation, because the universe is not just an empty space, but there are still some of the matter around. Maybe the accretion is important that would increase the mass and also spins further. And of course, the primordial black holes and population free probably have different mass spectra, and that would be interesting to look at. And then the next generation detectors also as a data scientist perspective, so it's kind of like a data challenge, because now you have to handle quite a lot of data in time series, and we need to build some sort of computationally efficient method to handle this large amount of data. Although it's not as large as the cosmological survey, but still is challenging in terms of parameter estimation that has to be consistent with the general relativity prediction in the waveforms. So I think that's it for my talk.
All right, thank you, Ken. Questions?
I missed one very simple point. When you do all this work on primordial black holes, what do you assume about the mass distribution of
Yeah,
those black holes?
that's a good question. So for that, so that's actually one of the reasons why we just try to do some of parameter estimation along a grid. So first, we know that the optimal system is around 20 to 40. So we put a log normal mass function that has a peak at 30, and then we have a spread that is, I think, so across like 10 solar mass to like 100 solar mass also for the rate study. Yeah.
So when you make an estimate of F, that F corresponds to that particular mass range,
Yes.
there could be a huge number of black holes elsewhere,
Yes.
and you're not constraining that.
Yeah, we are not constraining that. But of course, there are different methods to constrain lower and higher masses. So for lower masses or the subsolar masses, we can do some sort of like continuous wave detection. That is to say, because the subsolar mass, they have lower masses, and that is to say their in-spiral time is much longer, so they don't really merge even at the current time. So that would emit still very in-spiral, and then they can add up to a stochastic background, and then we can look for that using the stochastic gravitational wave background. And then for higher mass, and of course, there will be a LISA stuff that on the space, yes, on the space, and then you can look for that using LISA measurements, which is also next decade, I think. Yeah.
Questions? I have a question. For the lower redshift range, you mentioned 0 to 30, right? When
Yes.
There is uncertainty if there is a primordial black hole or a POP3 black hole. How does your ability to constrain the population, the properties of this population, depend on the probability of merging of these black holes? So we know that also for POP3 black holes, or normal black holes, studies on time delay between the formation of the binary actual merger is actually very uncertain.
Yeah.
So do you have any, how do you constrain this if you don't know the differential probabilities for merging?
Okay, so what I'm doing now is really just map the end result, that's the merger rate density. Mm-hmm. So if we want to map back to the, so if you want to extract further what's the binary fraction or probability that forms the binary black holes, then we probably need, at least for the population-free, we probably need more EM observations that at least constrain what's the population-free star formation rates first. And also the initial condition, which may be doable with TS or like JWST. And then with that, then you can extract the probability of the binary formation, etc. And of course, you can still do some, so with the merger rate density, and then you assume some phenomenological models for the star formation rates, or from your simulations, then perhaps you can extract some of the information purely with gravitational wave measurement. But I think that would be, your end result would be very unconstrained, because usually like you are really using a curve that tries to constrain a higher dimensional space that controls all your astrophysics. And if you just look at the merger rate density, it would be, I don't think it would be very well constrained. So I think there is, so in fact, there would be like much room for the electromagnetic and gravitational wave synergy there to extract more astrophysics there. That's what I think. But of course, the first step is that we still need to quantify how well we can measure the merger rates, right? Because otherwise we cannot even do a synergy there.
Thank you. Any other question? All right. So let's thank Ken again.